Hello, this is Joseph Bakos, welcoming you back to the Taurus Report, the bull in the china shop of cosmology. So, last week we went into how CGC works and how it explains where gravity comes from, what causes gravity. And so it is depicted basically as a relic of electromagnetic radiation. And the first thing that someone might ask for if they're considering whether this theory is true or not is there any indication right here within our solar system that gravity does not behave as predicted? And it turns out there is actually quite a lot of evidence here in our solar system that under certain circumstances gravity does not behave as expected. And so I would like to go over some of those and share them with you. The first one we took a look at already, which was sort of new, the Oumuamua asteroid. As it came through our solar system, it did not follow a path that one would expect based on standard theory of gravity. Another one is the Pioneer anomaly. So Pioneer 10 and Pioneer 11, both of them, once they got beyond Pluto, they seemed to suddenly be pulled by the sun more than expected. And so NASA spent something like 10 years trying to figure out what was causing this unexpected acceleration. And they came to a conclusion which I disagree with. Eventually, they came to the conclusion that it was caused by heat is escaping from the spacecraft in a, they call it anisotropic way. All that means is normally you'd expect heat to be radiating kind of roughly uniformly from an object. So they concluded that heat must be radiating more from one side than the other. So, for instance, if the spacecraft is traveling away from the sun, heat was radiating from the spacecraft in the forward direction, causing it to decelerate more than expected. Now, I disagree with that in the sense that you can model heat escaping any which way you wish, and you can keep playing with your model until you finally get it to be escaping in this unidirectional way, and then claim that you've accounted for the deceleration. Well, how would you go about proving that that is what happened? So I would say the Pioneer anomaly, that's kind of iffy explanation. But there are a few others. Another circumstance where we have this same sort of anomalous acceleration would be comets. Now, as we've discussed previously, because comets they travel in this very eccentric orbit, so that much of the time they are traveling with high velocity, more or less directly at the sun, because their orbit is so eccentric. It's not like a nice circle, it's more of a very elongated ellipse. And so, according to CGC, that would cause anomalous acceleration, because the only time you'd see a very steady force of gravity would be if you're in an approximately circular orbit. And this happens because of acclimation, as we discussed in the previous episode. So a comet does show anomalous acceleration, and it's called non-gravitational acceleration. And current theory assumes that it is caused because the off-gassing from a comet, they assume it to be directional. Now, once again, I think that this is not true, and I think that the off-gassing from comets is roughly spherical or roughly equal in all directions, maybe not exactly equal, but equal enough that the anomalous acceleration we see with all comets is not caused by the off-gassing. It is instead caused by the very high radial velocity. So again, radial velocity means, like if you have a central object like the sun, a radial velocity means that you're heading towards the sun sort of like in a direction that would be akin to a spoke on a wheel. So you're heading towards the sun. That would be like radial velocity, whereas orbital velocity would be if you're going in a circle around the sun. Now a comet, because of its elliptical orbit, is heading at high radial velocity often, and so according to CGC, you would expect to see anomalous acceleration. Now, there are a few more examples of this right here in our solar system, and one of them is the flyby anomaly. And this happens occasionally when you have some sort of either satellite or spacecraft that travels at high radial velocity again, like when spacecraft are trying to take advantage of the slingshot effect. Sometimes a spacecraft, we will deliberately have it, like if this is the planet, we'll have the spacecraft come very close to the planet and sort of whip around it and take advantage of the gravitational force of the planet, sort of like a slingshot effect, to gain some speed coming out of that. And they find that oftentimes when we do this with spacecraft, we end up gaining more speed than we were expecting. And this cannot be accounted for under standard theories of gravity. And so this would make perfect sense under CGC, because once again you have an object going at high radial velocity. Another interesting case was the Russians experimented with putting satellites in what are called Molniya orbits. And in Molniya orbit, you can see the picture right here. Let me click on this picture here. So a Molniya orbit is very elliptical, highly elliptical like this. And we can see in a Molniya orbit, the Russians, they had difficulty keeping this orbit stable. Now, under Newtonian or standard gravitational theory, there's no reason why a very elliptical orbit like that, there's no reason why it should not just stay stable. In theory, you should be able to have an elliptical orbit like that, tracing out approximately the same path in every cycle, and it should be able to be maintained in a stable way, just like a circular orbit. Now, CGC says that is not the case, because you get variations in the phase of gravity, and I'll get to that in a moment, so that anything traveling at any kind of high radial velocity, as they would do in a very elliptical orbit, that is going to introduce instabilities. And so I posit that the reason why the Russians were not able to stabilize those Molniya orbits was because gravity behaves according to CGC and not standard gravitational theory. Now, when these sorts of anomalies show up, theorists trying to explain it with standard theory will come up with various explanations about how either the moon or Jupiter or some other object is destabilizing the process. And again, I think that depending on your assumptions, you can create a model to try to explain each of these things. But I think that understanding gravity from the perspective of CGC explains them better. Now, there are a few other interesting things in right here in our own solar system that shows that gravity varies in a way that current theory cannot explain, and I will go over a few more of those in a moment here. As discussed in the last episode, I'm proposing a new force law for gravity that looks something like this. And this force law means that we end up with a kind of a waveform, two different waveforms. First, we get sort of a random waveform when a system is first forming, or if, let's say, you had the breakup of some large mass. So it's all breaking up, and suddenly you'd have this sort of randomized pattern. Now, on the vertical axis here is the force of gravity, and so a positive force means an attractive force. I'm calling the attractive force positive, and then anywhere below the x-axis here, below the horizontal axis, would be a negative force, showing that gravity can be repulsive sometimes. So when a system is first forming, like when the solar system was first forming, the waveform for gravity would be both positive and negative and sort of random like this. And as I discussed again in the last episode, an early solar system would look something like this. It sort of looked like the ring system of Saturn. And so this is H.L. Tauri, and I am claiming that the dark areas where there is no mass, gravity is either weaker or else repulsive, and the bright rings are areas where gravity is stronger because of this randomized waveform. Now, after a body gets acclimated and is in circular orbit, over time, two bodies become acclimated and adjusted to each other, and you end up with the waveform of gravity looking more constant like this. So here's a more constant, attractive force law for gravity. And so if we adapt this kind of thing to the solar system, now right now in these two graphs that I made, it shows the force of gravity varying over time. So time is on the horizontal axis. Now the interesting thing is that if you adapt the force law so that distance is on the horizontal axis, you end up with the same sort of look to it, the same sort of variation. And so I do an adaptation of this here. Again, as shared in the previous episode, I just want to run over this once more here. So here the blue line would be a force law according to CGC, and the purple line would be gravitational force according to standard theory. On the horizontal axis is distance, and on the vertical axis is how strong the force is. And here the green dots are the planets. I put Oumuamua here, showing that CGC can account for Oumuamua. And then Mercury, Venus, Earth, Mars, and then Ceres. And so when we see gravity varying like this, this means that under CGC, when we have slight variations in the gravitational force law, like with these various anomalies I've been mentioning, Oumuamua, Pioneer, Flyby, Molniya orbits, comets, all those things that I mentioned, CGC could account for those things. Now I'm going to move on to speak about the asteroid Bennu in 2020. I think the OSIRIS spacecraft went to the asteroid Bennu and found some very surprising things there. One thing I'd like to mention about CGC, one result of it, is it means that all masses, whether you're talking about asteroids or you're talking about planets, you're talking about comets, You're talking about stars, suns, galaxies. All masses would have certain discrete sizes and arrangements that are stable. And then if you go outside of that, they would be unstable. And in my opinion, this is why most of the solar systems in our universe are binary, meaning you have two stars orbiting each other. Because normally what happens is the amount of mass in that region isn't at a convenient amount of mass. In other words, it's either a little bit too much or a little bit too little to provide one of those stable sizes for a sun. And so anything that is excess, what it means is that that amount of mass, the surface of that mass would be at a distance where gravity was repulsive. And if the surface is at a distance where gravity is repulsive, then that mass is going to be unstable. And this is why solar systems end up being binary. Like if there's too much mass, some of it gets ejected to form another star. Now, one bit of evidence for this is what we saw when we went to Bennu on the Osiris mission. I'd like to share some of that with you. So why is asteroid Bennu ejecting particles into space? On the surface of Bennu, for some unknown reason, different pebbles and rocks would like shoot off spontaneously into space. And once again, theorists sort of guessed maybe that there's like frozen water on Bennu, and when it faces the sun, some of the water vaporizes, causing an explosion, ejecting rocks into space. But once again, I don't think that that is what's going on. I think the asteroid Bennu happens to be at one of those inconvenient sizes. And there is some confirmation of this in another anomaly they found on Bennu. Is when they went to land on it, they were expecting like a firm surface, and that is not what they found on Bennu. Okay. Another surprise, they found that the surface is like a plastic ball pit. When they tried to land the Osiris spacecraft on the surface, it started sinking in just like it was going into a ball pit. And what does this mean? So to me, what it means is that Bennu is at one of these inconvenient sizes where the surface has extremely weak, or at the very surface where there's very small pebbles and stuff, even negative gravity. And this is why Bennu sometimes ejects particles into space. Eventually, over time, either it will form two different objects, or ejected particles will get lost, or it will end up conglomerating with more asteroids and debris from around it until it reaches a more convenient size. But in my opinion, what we observe happening at the asteroid Bennu is evidence in favor of a CGC version of gravity. Another example is Saturn's braided F-ring. This shows something that CGC predicted. I predicted with modeling here in a video that I posted a few years ago here, 2019. I was modeling gravity as a waveform. And so I did a solar system model and showing how it would develop over time, and over time the orbits would stabilize because of acclimation. But here, let me fast forward it where we're covering, tens of thousands of years of motion, and we can see that before acclimation we get all sorts of weird orbits going on. And then gradually, over time, they acclimate. But the thing I want to point out to you is that early on, you get these sort of sometimes waveform orbits. So you'll get braids and waves in the orbits because of the way that gravity varies under CGC. Now, interestingly, we find something like that when a asteroid or small moon or something broke up in Saturn's orbit, and it provided this braided F-ring of Saturn. And once again, in all of these videos, all of the links that I reference, I will include in the comments if you would care to look at these links yourself. So this F-ring of Saturn, and I'm not sure if it's still braided because, as I said, after acclimation, I expect things to go more in a circular way, but for a while this ring of Saturn was showing this sort of braided wave-like action. One of the things that critics of CGC have asked for is the ability to explain gravity right here in our solar system. They ask, can CGC work as well as Newtonian or general relativity to describe the accelerations of objects within our solar system? And the answer is yes. Yes, it can. And from this, we will move in the next episode. We are going to look at the biggest known gravitational anomaly of all, which is galactic rotation rates. When scientists first started looking at galaxies, they noticed something odd, and that was that the stars in the outer edges of galaxies, they are moving too fast. So at those speeds, they should be flying off into space, but instead they're held in orbit around the center of a galaxy. And so this is rather a famous diagram showing the velocity of observed stars orbiting around a galaxy as they get further and further away. So this is the distance in light years along the horizontal axis here, is the distance in light years from the center of the galaxy. And then on the vertical axis is the velocity that those stars are traveling at that distance. Now right here, this dashed line, this shows what would be expected if gravity behaved according to Newtonian or general relativity. This dashed line is what we would expect to see. And instead, what we see is this observation line up here, this flat rotation curve. And so this is the thing that presented such a problem. It presented such a problem that theorists introduced the idea of dark matter in order to explain it. The basic idea is that a galaxy contains mostly dark matter, which is matter that cannot be detected at all except by its gravitational effects. And so every galaxy is posited to be made up mostly of dark matter in order to explain that flat rotation curve. However, under CGC, because gravity can vary by quite a bit, so if we go back to this graph here, we see, and this is an example in our solar system, but the same thing applies whether you're talking about a solar system or a gravity or a galaxy. You can get odd zones where gravity is much greater than expected. And because it is a waveform, it might actually result in something like this, where this region is kind of the top of a wave from the waveform. But in any case, we shall discuss galactic rotation rates in more depth in our next episode. So this is Joe Bakos saying goodbye from the Taurus Report. Thank you very much for watching, and we will see you again next week.